Very privileged to have you here visiting us, Dr. Fisher, and at this point I'll turn the mic over to you.
Okay. Thank you.
Thank you.
Yes, I should put that somewhere. Thank you, and good afternoon, ladies and gentlemen. It's indeed a pleasure to be here to discuss on this particular topic, which is one that is dear to my heart. When we talk about fatigue and fracture, we should not just think of our contemporary world today, but we must think of the fact that these problems surfaced in the 1800s, in the early days of mining, in pressure vessels and storage tanks, in railroad bridge members and railroad car axles. So it was those conditions that led to the early studies in fatigue, the first published papers you will find going back into the 1850s. And of course, during and after World War II, it was in this era that in the United States, at least, the growth of welded construction took place. In fact, if you drive around New York or any state, you will find that prior to World War II, there were very few welded structures. So we will deal with that. I will just cite here the fact that there were early welded bridges in Europe, particularly in Germany, Belgium, and France in the 1920s and early 30s. And because of the quality of steel, most of those structures failed almost immediately after being put in service during cold temperatures because of the cracks that had been introduced during the welding process. And in fact, it led to a rule that was adopted in the United States back after World War II that one should not weld transverse to the tension flange. And during the course of this talk, I will point out that that adoption is one of the greatest sources of fatigue cracking that we have in our nation. So you should be careful of what you think is a proper solution to a problem, then in fact you may be introducing a solution that is worse than what you had prior to that. Now in the 1960s and before, it was very common. If you look in the literature, most of the studies that were carried out were on small specimens because of the capabilities of the experimental work that was carried out in the U.S. and abroad. And so the limitations of machines led to very simple tests. And they were very small, and as a result, fatigue is a time-dependent phenomena. It takes many cycles to achieve crack initiation, growth, and failure, and therefore in the 30s and before, or 40s and 50s, it was not unusual to carry out only a few tests and then construct what goes back to the time of Wohler in the 1850s, what we in the United States and elsewhere in the English-speaking world commonly call a stress life diagram, SN curve. So the focus in most of this work was on maximum stress because the most common fatigue design until 1974 was the use of the maximum stress and to penalize the maximum stress as a function of the R ratio, which I will talk to you about shortly. Now the early fatigue work that initiated most of what was subsequently done in the United States can be attributed to the Asheville Road Test steel bridges. These were loops that were constructed in Ottawa, Illinois, and in which in the late 1950s and 1960, trucks driven by military personnel circled these test tracks and subjected these real bridges to actual stress cycles of known load. And so it was during the course of these tests that cracks formed at cover-plated beams in approximately 500,000 cycles of truck loading on bridges that had been designed in accord with the AASHTO specification at the time. So that indicated there was a potential problem, and it subsequently led to a substantial amount of work that was sponsored by the National Cooperative Higher Research Program, and I think you've heard in an earlier lecture this semester about that problem, about that agency. Now, I said that the maximum stress was controlled, and it was controlled by what was commonly has been called the Goodman diagram, or sometimes the AWS diagram. You can see this diagram, which I'll show you in the next plot, is that the maximum stress is a function of the stress FR0, which is the stress range at R ratio of 0. The R ratio is, as you can see here in the lower portion of this slide, the ratio of the dead load stress to the maximum stress, which is the sum of the dead and live load. Now that means that along a bridge, that ratio changes. And so that was one of the complicating factors. And so this concept of design, which I should say is actually used even today in some industries worldwide. For example, machinery design makes use of the Goodman diagram, and I have seen the failures that result from it. So this process of design, in my opinion, is a very poor process, and it was attributable to the fact that most engineers who used it didn't understand what it meant. And so the understanding of fatigue was not very good. If you looked at this graphically, it's nothing more than a plot of the maximum versus minimum stress. And of course, the stress where the minimum is equal to the maximum is just a stress without any cycles. It's essentially a tension stress or compression if you're going into compression. And so you can see that it had two coefficients, K1 and K2. K1 was one related to the material properties. Because of these small tests, it was thought in 1960, on the basis of some work done in Germany, that the higher the strength of the steel was, the higher its fatigue resistance. Now that was not true, but that's what the fact that tests on small specimens, comparing tests that have been done on mild steel earlier decades, they thought that the fatigue resistance was improved by material, by going to a higher strength material. Now, the AASHTO code that was invoked at the time in the 19s, and in fact, it was until the AASHTO code did not directly refer to fatigue until 1965. It was in 1965 that the California Department of Transportation sort of put together a draft specification based on the database that existed at that point on these small specimens. It used maximum stress, which obviously varied. There were different equations when it went into compression. They had categories that were